Good day to Dr. Gan Kang-hoon. We are from Group 17 and in this video we will be explaining about morphological analysis in natural language processing using finite state machines. This video is presented by Sindhuja J. Kumar, Pointana Ainamutirian and me myself Dinesh Kumar Saravanan. So what is morphological analysis? Simply put, it is the study of the structure and form of words in a language, including the ways in which words are formed through the combination of morphemes. Morphemes can be broken down into roots, prefixes, and suffixes. For example, if we take the word unhappiness, it can be broken down into three morphemes. The root word will be happy, the prefix will be un, and the suffix will be ness. So why is morphological analysis is important? Morphological analysis can be used in various applications in NLP such as text translation, information retrieval, speech recognition, and text parsing. The motivation for employing finite state machine is because to prove the capability to handle complex linguistic phenomena with precision and flexibility. For example, the finite state machine based morphological processor developed for Spanish successfully manages inflectional and derivational changes across tens of millions of word forms, and it showcases the model's capacity for handling substantial linguistic data with minimal performance overhead.
FSM in computational linguistics. Finite state machine FSMs are computational models used to represent and control the execution flow in system. An FSM is characterized by five different things: a finite set of state Q, a finite set of input symbol sigma, a transition function delta, an initial state Q naught, a set of SF state F. FSMs process text by transitioning through states according to morphological rules, identifying and annotating elements like roots, prefixes, and suffixes. They are particularly useful for languages with straightforward linear morphologies. Problem statements. Here are the few problems that can be identified when developing morphological analyzer using FSM. Firstly, integration with existing system. FSMs are hard to integrate with existing NLP frameworks, often needing more major changes to work effectively, which complicates their adoption in older systems. Secondly, handling complex morphologies. FSM work well for regular morphological pattern but struggle with complex or irregular morphology or rich languages, especially in languages with high inflection or agglutination. Thirdly, adaptability to new linguistic rules. Adapting FCM model to new languages or evolving linguistic rule is challenging and requires significant manual effort, limiting their flexibility and quick adaptability. And lastly, generalization across languages. FSM models need extensive customization for each language, making it difficult and resource extensive to deploy them rapidly across multiple languages.
We will look at our proposed solution for morphological analysis using finite state machine. This slide is divided into two main sections: lexical structure and compilation of morphological and phonological rules. First, let's explore the lexicon structure. We first start with root lexicon. The root lexicon stores the base form of words which are essential for identifying the core semantic unit of morphemes. For example, in English, the root run serves as the base for the verb to run. This root is fundamental part of the verb and all other forms of the word are derived from it. Next, we have the affix lexicon. This lexicon catalogs prefix, suffix, infix, and circumfix, each annotated with their roles in modifying the meaning or grammatical function of root morphemes. For instance, in English, the prefix un in undo modifies the meaning of the root verb do to indicate the opposition action. Similarly, in suffix ing as in running is used to form the present participle of the verb run. The last component in our lexicon structure is the combined lexical entries. This section includes entries from commonly used compound words. In English, compound words like blackboards are quite common. Here, the combined entry includes the root black, an adjective, and board, a noun, to form the compound noun blackboard. Now, let's move on to the compilation and morphological and phonetical rules. First, we have the morphotactics rules. This rule specifically valid combinations of morphemes according to the language's synthetic and morphological norms ensure that the structure generated adhere to the grammatical rules. For example, in English, the combination of the root cat with the plural suffix s forms cats, a grammatically correct plural noun. Finally, we have the orthographic rule. These rules manage the spelling adjustment necessary when the morphemes combine with to form words. These include modifications like consonant doubling, vowel changes, or the introduction of silent letters aligned with phonological changes. In instance, in English, when we form the present participle of run, we add the suffix ing resulting in running. This rule ensures the doubling of the consonant n in the verb form to maintain orthographical integrity. Now, we will look at the system architecture of this analysis. This slide outlines the three levels of finite trained transducers involving lexical, morphological, and orthography. The first level, the lexical FST, manages the decomposition of the input string into their constituent morphemes such as roots and affix. It utilizes a lexical database and optimizes search algorithm like a trie structure for rapid matching. In English, the word running is decomposed into the root word run and the suffix ing. The second level is morphothetical FSC, assembles recognized morphemes into valid linguistic construct. It checks for correct prefix, root, suffix combination, ensure syntactic continuity in terms of gender, number, and cases. The word cats ensure that the plural suffix s is correctly attached to the noun root cat. The third level, the orthographic FST, adjusts word spelling to account for phonological changes. These include modifications such as consonant doubling, vowel changes, or introduction to silent letter based on specific language orthographical rules. The word running involves adjusting the spelling by doubling the consonant n in run. These three levels of FST works together to ensure accurate morphological parsing by progressively refining the structure and spelling of words according to linguistic rules. This structure approach is crucial for effective natural language processing (NLP). This is an example image of the system architecture. The system architecture image clearly defines as such. First, noun and verb lexicon. The separate lexicons for noun and verb feeds into their respective morphological and orthographic rule sets. Second, the morphotactic and orthographic rules. The rules are set applied sequentially to ensure correct morphological parsing and orthographic adjustment. Finally, the MAC model. The morphological analyzer grammar, which is known as MAC model, integrates the output from the noun and verb parsing part, combining them into unified analysis. The system employs sequential processing across the three levels of FST to ensure that each stage is morphological analysis is performed in a logical and orderly manner. This sequential approach allows for the structure breakdown to input string into morphemes and application of morphothetical rule and the adjustment of orthographic forms. Additionally, parallel transducers are employed specifically at the orthographical level to handle spelling checks and adjustment. This parallel processing enables the system to simultaneously apply multiple orthographic rules, ensure that the final output is orthographically correct and adhere to language specific conventions. The combination of sequential and parallel processing enhance the system effectivity and accuracy, allowing for comprehensive morphological analysis that is both detailed and robust.
Now, moving on to the next part, framework of the proposed solution. There is 6 steps in this framework. The first step is input processing and normalization. This step converts all the words to lowercase and remove any diacritical mark, for example, accent marks, ensuring that the input to the FST is uniform and ready for further processing. As you can see here, the input text had uppercase and as well as accent mark and it has been removed in a normalized text. Second step is tokenization. Tokenization is the nominal text is split into individual words based on spaces. This process defines the units for subsequent morphological passing. So from the input text, we can see here there had been 5 tokens. Now the third step would be morphological passing, lexical FST level 1. The lexical FST identifies the root word coda and recognizes the conjugation suffix iamos, preparing the token for syntactic and morphological integration, as you can see in the example provided. Now, moving on to the fourth step, morphotactical integration, morphotactical FST level 2. This stage validates that the root and suffix combination conforms to Spanish verb conjugation rules, ensuring the grammatical correctness of the verb formed. As you can see here, we have used a Spanish word. The process token was corriamos, and now the example is showing two different things. And in step 5, the orthographic adjustment will be done. Orthographic FST level 2. The orthographic FST reintroduces the accent mark on the I, which is necessary due to Spanish phonological rules governing stress in verb conjugation. This adjustment ensures the written form matches standard orthography. For example, the initial form had no accent form, but the adjusted form has accent form. And lastly, step 6, output generation. The fully processed token is output as a structured morphological representation, providing a clear breakdown of the word's root, tense, and person. This output is crucial for NLP tasks such as syntactic parsing and semantic analysis, as you can see in the example and the final output given here. Scope of solution. The proposed FCM based morphological analyzer is designed to address a wide array of languages, leveraging its modular and adaptable architecture. Firstly, versatility and modularity. The analyzer solution is designed allowing each component, such as lexicons, morphotactic rules, and orthographic rules, to be independently developed, tested, and updated. This modularity facilitates the integration of language specific features and rules without overhauling the entire system. Secondly, primary focus is on well documented languages. The system focuses on languages with well documented morphological rules. These languages provide a robust foundation for developing and testing the analyzer as the grammatical structure and morphological patterns are well understood. Next, extensibility for additional language. While the primary focus is on well documented languages, the framework is inherently designed to be extensible. This extensibility is critical because each language has unique linguistic features that require tailored solution for accurate morphological analysis. The reason behind choosing FST is because of its own advantages. The choice of FST, particularly multi-level FST, is justified by the ability to efficiently model the layers of language processing required for accurate morphological analysis. This approach allows for, firstly, modularity. The system's modular architecture allows for easy updates and integration of new languages or linguistic rules. Each module can be independently developed and tested, ensuring flexibility. Secondly, scalability. Designed to accommodate multiple languages, the system can be scaled to include additional languages and linguistic complexities over the time. And thirdly, efficiency. The use of FSTs enable efficient processing of input strings, making the system suitable for real-time applications. Disadvantages of using FST. Firstly, complexity in rule creation. Developing detailed morphotactic and orthographic rules for each language can be time consuming and requires extensive linguistic expertise. Secondly, handling highly irregular language. Languages with numerous irregular forms or those lacking well documented grammatical rules pose significant challenges, potentially limiting the system's effectiveness without substantial customization. So, to conclude, morphological analysis is a very crucial component of natural language processing as it involves breaking down of words into smaller, meaningful units to understand their grammatical structure and meaning. This process is essential for numerous NLP applications, including text analysis, machine translation, and information retrieval. Extensive research has demonstrated that for morphological analyzer, FSM is the best solution. So, the proposed solution in this paper would be employing FSM to manage various morphological processes, ensuring precise parsing and analysis. This system's modular design allow it to be easily extended and adapted to accommodate additional languages and unique linguistic feature. That's all from us. Thank you.